When working with solution in chemical laboratories, we are often required to dilute a solution with a known concentration to a lower concentration by adding solvent. This process is known as dilution, and it involves the addition of a solvent to lower the concentration of a solution. In aqueous solutions where the solvent is water, that means that we're adding water to lower the concentration of a solution. And typically we want to dilute the solution to a specific concentration value. The key here is to realize that the amount of solute in the solution does not change when we add the solvent. So in other words, the initial moles of a solute in a solution prior to adding the solvent, we can term that moles initial or moles I, that equals the final moles of solute in a solution after we add the solvent. So in other words, moles I equals moles F, or moles initial equals moles final. And we know now from our molarity equation that we have an expression for moles. Moles equals molarity times the volume expressed in litres. And so we can take this equation here, moles initial equals moles final, and substitute molarity times volume in for each of those moles expressions. So the initial molarity times the initial volume will equal the final molarity times the final volume, or MI/VI equals MF/VF. And this is the dilution equation. Sometimes you'll see it as C1V1 equals C2V2, where the C1 is referring to the initial concentration of the stock solution, and C2 is the final concentration of the diluted solution. So let's look at a typical scenario in terms of dilutions. We're asked to prepare 350 milliliters of 0.12 molar copper sulfate solution from a stock solution of 1.5 molar copper sulfate. Now, a stock solution is a solution of known concentration, and it's typically stored in the laboratory, and we take stock solutions and we work with them, typically by diluting them. Stock solutions tend to be fairly concentrated. So we'll use our dilution equation. The initial molarity times the initial volume equals the final molarity times the final volume. So the initial molarity of the stock solution is 1.5 molar. The initial volume that we want to extract from that stock solution is unknown, and in these dilution calculations, this is what we're actually trying to determine. We're trying to determine what volume of stock solution we want to extract to get our 350 milliliters of 0.1 molar copper sulfate. We know that the final molarity that we want is 0.12 molar, and we know that the final volume we're after is 350 milliliters. So we can substitute all of those values into that equation there. We can make the initial volume the subject of that equation, plug those numbers into our calculator, and what we get is an initial volume of 28 milliliters. So in other words, what we're doing here is we're starting with a 1.5 molar stock solution of copper sulfate. We extract 28 milliliters out of that stock solution, put it into another container, typically a volumetric flask, and we would add, in this case, 322 milliliters to take it up to the total of 350 milliliters, and what we end up with is 350 milliliters of 0.12 molar copper sulfate. So the dilution equations shown here are very useful in being able to determine exactly how much stock solution we need to withdraw in order to make up a specific concentration with a known volume. And just please remember, only use these equations for dilution equations. Sometimes we see these used in solution stoichiometry and it can get a bit confusing. These two equations here, only for dilutions.